Okay, so the next presentation is by Spliet. It's gonna it is GSOC, not GSOC, EVoC project. So the EVoC is the equivalent of the Google Summer of Code, but for from the foundation, the X.Org Foundation. So it's sponsored by the X.Org Foundation, and it's basically the GSOC, but unlimited. You can start at any time during the year. It's not limited to summer. So the name is Endless Summer of Code. Not summer, Endless Vacation of Code. Sorry.
Okay. I'm afraid I do have a slight technical issue with the screen right now. Because all of my half is missing. So let's just see if I can get... Anyone knows what this tool is actually called? GNOME settings? The control panel? Or? Okay, maybe it's just around here somewhere. There we go. Yeah. That would hopefully do the trick. Oh, excellent. Go. Really? We may need to run it. Sorry? We may need to run it. That might make a difference, actually, yeah. So first of all, I would like to thank you all for coming and apologize in advance for kind of distracting you here with a time demo of Portal. But I wanted to start with this to give a bit of a point at which Nouveau used to be in terms of performance. Now, I'm not actually seeing it play, so I'm hoping it's still low. And if you look at it, and if you look at how the movement of the player goes. I'm not sure about you guys, but the first thing I was thinking is there must be a way of playing this faster. It probably is, but it's so boring that I want it to be faster and faster and faster. And, well, kind of jokes aside, one of the major problems that we've had with Nouveau up until now, and one of the major criticism is that performance was not up to speed with any of the other drivers. And it inspired me to start working on a X.Org endless vacation of code project in reverse engineering the clock tree and the miscellaneous clock inside an NVIDIA GPU. And I'm afraid I have to finish this one before actually going to tell you why this clock tree really matters. So I'm sorry for the delay here. Shouldn't take long. It's about a 2-minute demo as far as I know. Sorry? Come on, you can do it. You can jump. There we go. It does render fairly correctly, so that's not the issue with Nouveau. It's actually, in terms of image quality, quite impressive what has been done with reverse engineering efforts. So I can actually, no, I'm actually going to spoiler it right now. It's finished as far as I know. And it's going to tell you that it ran at about 23 frames per second. And if I now start this presentation correctly, I'm sorry about this, guys. Apparently Portal changes my display settings again. So I'll just set it that way, and there we go. And now you can see it. So why do these clocks actually matter? Well, this is actually really simple to explain. If you look at the DMESC output of booting, it will tell you that the Nouveau driver supports several clocks. It has like a low mode, a middle mode, and a high mode. And it boots by default in this middle clock range, which is close but no cigar. It actually gives you some sort of performance, not all that the device is graded for. And it's burning through more power than it really needs to when you're not doing anything. So if we are able to change these clocks on the device, then there must be quite a performance improvement. So I'm going to tell you it's really briefly why this is more challenging than regular reverse engineering of graphics cards. Just by a simple example, Then I'm going to tell you a bit about the process of reverse engineering, and I'm going to try to not give too much hardware-specific details, because you can all look that up in our documentation. After that, I will share you some results and future work and answer some questions afterwards. But first, a challenge. So if you are going to reverse engineer a regular graphics-oriented workload, like something simple, like draw me a red triangle, you're going to make the, well, in our case, make the official driver actually draw a red triangle, then intercept this communication and try to replay it. And if you replay it correctly, you will see a red triangle. Sometimes you don't. You see something else, like a blue circle. And then you're going to tweak the output, the inputs a little, and hopefully, eventually, you end up with a red triangle. So you have this visual means of verifying that whatever you just fed into the GPU actually means what you wanted it to mean. However, with clocks, you don't have this visual helper. You don't have this visual aid here. It's either going to give you the image that you already had, or it's going to give you absolutely nothing and crash. Or, well, slightly in the middle, it might give you a really bad, ugly screen full of pink and purple and other colors that it's not supposed to be when you have a blue desktop. And this makes it challenging, because it's really hard to find the reason why your reclocking action didn't work. It's not giving you any visual aid here. So how did we do this? How did I tackle this problem? How did my predecessors tackle this for some other GPUs? Well, step one is really actually understanding the clock tree. The clock tree in an NVIDIA GPU has several layers. It's kind of hierarchical. And there are many ways of bypassing certain steps in the hierarchy. And there's a lot of control registers that we wanted to understand. And a big aid in understanding this is the cycle counters that we've had. Someone previously reverse engineered cycle counters, and really this helps us understand the speed of certain clocks in the system. And if I tweak a little bit in one of the registers, it will actually show me what the result is. And this helped me understand the routing around this clock tree. So not only does this help to map the registers of the clock to the actual clocks inside the system, it also helped me map the clocks to a video bias entry. Of course, again, and I can't stress this enough actually, that you can't do these kind of projects without proper tooling. We have NV tools, as Samuel already told you. It's a big collection of documentation and tools to read out cycle counters, to mess around with the GPU. There's a lot of documentation. I'll show you some other things as well. One of the tools we actually have is parsing this blob of video BIOS, which seemingly is just a lot of data, into its actual meaning, which is apparently a table that describes the various performance levels that you can actually set on this particular GPU. Again, we have a tool in NV Tools to actually take this video BIOS. And the mapping on the right in the comment section was actually derived by using these cycle counters. So step one was understanding the clock tree. And then there is step two, generating parameters. Now, this sounds a bit vague, and for me, partially it is. But especially when it comes to changing the clocks of the memory, there's actually quite a lot of parameters, some of which we understand. Like RAM timings can be fairly understood and well derived. There's some other features on RAM that help with the reliability of the actual RAM chips, like ODT and DLL. There is some link training going on, even on these cards, that we wanted to, make sure we do the same process. Otherwise, the card would crash. And there's a whole lot of bits. I have no idea what they're doing. And the only strategy that we could follow here was actually just mimic the official driver as good as we can. So what we do generally is capture something called MMIO trace. It has been mentioned before. Really briefly, we intercept all the MMIO communication between the official driver and the device. And then we store this in a big log. And again, NV Tools then contains a tool which holds the trace against all the register level documentation that we have and parses it nicely so that it's somewhat readable So that here you can see a bit where we change the video clock, and then a PLL coefficient is being read, and well, some other bits. And what we found in this trace, one of our, what we found really lucky is that NVIDIA not just directly pokes at registers to change these clocks, but for memory, they actually invented a sort of scripting language which they use, and they upload this script to the GPU. Scripting language has a quite complete ISA, which helps us in such a way that we not only see the writes going to the memory and all the registers around it, but we also see the required delays. And for link training, we can actually read the procedure for doing this link training. So that was really cool. Thanks, NVIDIA, for that. And these scripts run on the GPU in such a way that they can actually cut off the bus and make sure that memory is not being accessed. So there's a functional aspect to this scripting language other than just helping us reverse engineers. So we had to reverse engineer this particular instruction set architecture as well. And so we did. And from that, we derived all these parameters. Step 3 is actually execute the script. Once you have the parameters, once you have the clocks, you need to implement it in like Nouveau and execute a script. Now, this script in like really coarsely looks like this. First, we reclock memory. That comes with a lot of steps. The first one is a bit vague, prepare. Now, I'll give you an example here. Sometimes if you set a clock on an NVIDIA GPU, you need a phase lock loop, a PLL, to reach the specific frequency that you want. Sometimes you don't. If you go from a frequency that doesn't require the phase lock loop to one that does, you can actually program the PLL in advance, make sure it locks, and save some time on the actual process. So after all these preparations have been done, we wait for VBlank. We do this because that will give us a window of time to actually change the clocks without having any memory accesses for scanout. As a result, we don't get a blinking screen if we have a single monitor setup. So when VBlank starts, we pause the engines as good as we can, set the clocks, set the parameters. There's some other subcomponents that need to be reset then, after which we just resume the engines. When this is done, we kind of repeat sort of the same process for all the other clocks, but we don't need this much preparation. We just disable interrupts, pause the engines again, change all the clocks and the voltages, and then we resume. When this script has been run, everything is done. Once the clocks have been changed, they're stable again. But actually writing this script takes a lot of iterations of making sure the parameters are rightly generated, making sure that the clocks you're setting are correct, etc. And this has been mostly the tedious bits that I've been focusing most of my attention on now. But once you get it working, the last step is generalize. Because if you get it to work on one particular GPU, then you still have a lot of other boards with different types of memory. We have DDR2, DDR3, GDR3. There's different configurations, different memory partitions, different memory ranks, or numbers of ranks, actually. And we want this to work on all these cards. So after this, you need to generalize. Make sure that the parameters you generate are flexible enough that they are generated from the data inside the video BIOS. And any assumption you might have made, like this looks like it's kind of static, be prepared to just completely change the code again if you try and port this to the next card. So I've given you a brief introduction to the process. I would like to talk a bit about results now. And well, the first result is that this pile of GPUs that you see here, reclocking works now. There's even a laptop underneath, that's this one. And I would like to actually show you how simple it works now. So there is a systemfs entry for the driver. It's been there for a while. There's been some discussion on the mailing list, which I'm going to ignore for the sake of this presentation. And it's going to tell you that right now the clock was running at 405 megahertz. I can just echo F into this P state, and if I read it out again, now we see that the clocks have actually been raised all the way up to the maximum 607 megahertz memory clock of 790. And if I now rerun this time demo, you will actually see a massive speed improvement already. So I'm going to let this run for a little and try to capture your attention for a little. I know that this is really distracting, but in the meanwhile, I can tell you about some measurements I've done together with the hackers from Tech Inc. on this particular laptop, which they allowed me to measure the power consumption. And what I've noticed is that for the entire system, if I clock it all the way back to the lowest performance level, I save about 0.6 watts. Doesn't sound like a lot. It's actually 8% for the entire system, which gives me an additional 20 minutes of battery life on this particular laptop. It's not as much as you would expect, because there's a lot of other features on this GPU that will make sure that it's not running at the highest speed when it's idle. Think of techniques like clock gating, power gating, etc. And, well, look them up if you don't know them. But they already save a lot of power, so the only real advantage from clocking back is that you actually change the voltage as well. So from what I can tell, the demo is now finished. And as you can see, it's now been running at 35 frames per second, which is an improvement of about 50%. Well, this is pretty impressive, and I've run a lot of other benchmarks as well. And I'm afraid I do have to fix my screen again for you to be able to read it. There we go. Fortunately, I know how to do this. I'm an engineer. But if I go into the results, just for the background, I've ran this on a fairly modern system with lots of RAM and really ancient GPUs like the ones I've actually used. This particular generation is about 4 or 5 years old. So it might sound like a bit of a useless exercise, but the findings we did here in the video BIOS, in the reclocking process, will actually aid in doing this on modern cards as well. So anyway, I ran these benchmarks on my system with Fedora 20, Mesa 10.1, and it's been the same throughout all, so we have a fair comparison. And if I look at the portal performances, I can see an increase for the G210m, which is a DDR3 card, of about 50%, 60% in speed. For the GT240 I have, which contains GDDR3 RAM, it actually doubled. I can see a similar pattern if we look at Zonotic benchmarks. We went from 7 to 12 frames per second on the G310, which is not really impressive, but it's a nice performance increasement. On the GT240, we went from 24 to 41, which kind of changes it from hardly playable to okay. To put this in perspective, I also ran this benchmark, the Portal benchmark with the official NVIDIA driver. And with the resolution I used back then, we went from 20 to 30 FPS. NVIDIA gets 47. So we went from about 40% of their performance to just over 60, 65. I haven't done the math particularly. So we're getting there. Now that I've shown you all the nice benefits that we've had and how it works, there is a lot of future work, unfortunately. And these are a lot of tedious technical bits that I haven't been able to figure out in the time I've had. For one, the GPU doesn't always pause nicely. So I can change the clock, and when it's changed, it works perfectly. But when there's a lot of load, a lot of stress on the GPU, and I change the clock, you will see, I notice that the GPU doesn't pause, not the engines pause, and they will crash if the memory just disappears for a second. So at the moment, we cannot change the clocks under high load on the GPU. Additionally, I've seen some visible corruption on the highest performance level with one DDR2 card that I've had. I suspect this is a bandwidth problem. I don't have the tools to actually figure out whether it is, but it really looks like it, because when I clock back, all the corruption is gone. And sorry.
Sorry, the watermarks in the display block probably need to be changed depending on the clock level.
Yeah, that is absolutely one of the possibilities, but we have no idea where all these watermarks might be. I mean, it could be a FIFO overflowing, it could be actual bandwidth problems, it could be a timeout that's set too strictly. There's all sorts of reasons why this could fail. I haven't been able to find it so far, and
another thing too that we ran into, and at least on our implementation too, is that depending on how long your VBlank is, you may be or maybe not are able to do a reclock.
Okay.
So depending on the mode too, you need to know what the timing is going to be to do a reclock and whether or not it can be done.
Right, right. Well, I would answer this question by saying that if we run out of the VBlank period, all we see is a black screen because it's unable to do the readout of the next frame buffer. But the card normally tolerates this. It's just very inconvenient for the user. So this is probably unrelated to the problem that we're seeing here with visual corruption. It's one of the things that we need to address and we need to investigate, unfortunately. Another one is that we are now postponing the link training process of the memory, of the DDR3 memory, because it should be done on boot, but it requires us to increase the clocks by quite a bit. And until we have all these other reliability issues figured out, we do not dare to do this on boot, risking that regular machines will actually lock up. And we'll get a lot of user complaints for that, whereas if we postpone it to the first reclock, the user knows explicitly that it's changing the clocks. So if it hangs then, it knows what happened. One of the other issues we have is GDDR5 reclocking. Unfortunately, I have a GDDR5 card, but it doesn't work for non-reclocking related issues. So I've just donated this card to our developer god here. Hopefully he can address these issues for me, after which we can go and look at GDDR5 again. For the same reliability issues, we don't actually do load detection for automatic clock voltage adjustments, because as long as we're not absolutely sure that this is stable, we can't bother the user with this. We can't risk locking up machines randomly and having all sorts of problems. So this is somewhere in the bottom of the to-do list. And I'm not really sure where to put Fermi, Kepler, and Maxwell on the to-do list. There has been some work in progress here. But of course, the newer generation cards are really important as well, because they often boot with even lower clocks than we've seen on the Teslas. And, well, not leastly important, these cards are used more nowadays. To conclude, we have actually seen that clock scaling is quite mandatory for speed. We can get 50% more performance, up to 100% in some particular workloads. The process is understandable. It's tedious. It requires a lot of tinkering and tweaking, but it is a well-defined process, and it can probably be done again for newer generations of cards. And it's very rewarding in terms of frames per second. So what I've showed you right now is a demo on a kernel which is a stock Linux kernel with a good 30 patches applied. These patches are currently in the pipeline for, I think, kernel 3.19. So this work should actually land, and users should be able to use it. But you can always try my tree if you want. Before I conclude, I would like to put out really bluntly that I'm also available for hire currently, because I really have a bridge the gap between now and the next academic year. So if you wanted me to do tricks like I've just shown you, or really anything in the heterogeneous system architecture space, please contact me. Please check out my resume on my website. Having said that, I would like to ask if there's any further questions.
You said that you're working on getting this working for newer GPUs. How new are we talking about? Like 1, 2 years? So
I haven't picked up any of the newer GPUs myself at the moment. But I do believe that one of the developers is currently working on getting Kepler support, which is like the previous generation of cards, so 1 and 2 year old cards, as far as I know. Fermi is like the one between this generation that I've just fixed and the Kepler ones. I don't believe we have a developer for that right now, but yeah, we're slowly getting there. And depending on how much Kepler actually differs for the even newer generation like Maxwell, we might see more and more improvements coming over time.
Any other questions? Very well. Thank you very much.